Every day, we witness people walking in the streets, talking, texting, listening to music, barely paying attention to their surroundings. Pedestrians account for 14% of all traffic fatalities in the United States. In the last decade, pedestrian deaths increased by 15%. In fact, municipalities have started painting look signs on crosswalks in cities like New York and San Francisco. Most fatalities occur when the pedestrian is crossing the street. Our focus is on detecting the events when a person is entering a roadway. When a distracted pedestrian approaches the street, our algorithm detects the event and warns him to watch for oncoming traffic. This steers the pedestrian's attention back to the real world. Our approach is directed at detecting road features that separate street and sidewalk. These are primarily ramps and curbs. For such detections, wearable sensors are best positioned on the feet. A large number of shoe-mounted sensors are gaining popularity for fitness purposes. We exploit the accelerometers available on these wearable units for ground profiling and crossing detection. For our prototype, we used an inertial sensor unit with accelerometer, gyroscope, and magnetometer. It communicates with a smartphone through Bluetooth. The shoe-mounted sensor can measure foot inclination at any given point. The inclination or pitch trace can be used to identify the different walking phases. This is the push-off, and the corresponding pitch trace is highlighted in the graph. Next is the swing phase till the heel strikes the ground. We are interested in the stance phase when the foot is flat on the ground. The pitch at this point reflects the slope of the ground. We extract the highlighted stance phase from the pedestrian's walking cycle. Let's first consider ramp detection. When this person walks on a flat surface, the pitch readings measure an inclination of almost 0 degrees. As he walks up the incline, each step measures a positive inclination of the foot corresponding to the inclination of the ramp. Looking at the pattern in a window of past pitch readings, the algorithm determines that the pedestrian is walking on a ramp. As he walks down, the measured pitch reflects the slope and gets back to 0 on flat ground. When the person walks on the sidewalk, the algorithm measures an almost constant pitch at each step. As he walks off the sidewalk ramp, the measured pitch changes to a large negative value, and the algorithm senses that the person is entering the street via a ramp. Pedestrians can also enter the street by stepping off a curb. Let's look at curb detection. As this person walks on the sidewalk, the accelerometer magnitude measured at each step does not vary much. But when he steps off the curb, the force on the foot exhibits a sharp peak as shown in the graph here. What happens in the real world? We went down to one of the world's busiest pedestrian intersections. We evaluated our system at Times Square in New York City. Our path in New York City started at Times Square, went up to Central Park, and back to Times Square. Let's move on to our next test location. We also verified the performance of our system in a different urban environment in the Italian city of Turin. Unlike Manhattan, Turin has many cobblestone ramps. GPS positioning poses difficulties for street-sidewalk distinction. The blue and green traces were collected when the pedestrian walked along the red path. We can see that in such urban canyons, modern phone GPS receivers frequently reach errors of 30 to 40 meters and does not help us. Let's evaluate our shoe sensing approach. As the pedestrian walks along the yellow path, a correct detection is denoted by the green marker right before the person enters the street. As he exits the street here, a false detection occurs as shown by the red marker. All the subsequent entrances are correctly detected before the person enters the street. In New York City, our system achieves 90% detection rate with only 0.7% false positives across multiple test paths. In Turin, our system achieves 90% detection rate with 1.5% false positives. As our lives become more entwined with technology and the number of distracted pedestrians increases, this simple and effective approach will remind you to look up, put your phone down, and walk safely.